This is a continuation of the chapter on solutions, and today we're going to be looking at concentration of solutions, different way to express that. So the concentration units we're going to be checking out today are mass percent, which is the mass of the solute in grams divided by the mass of the solute plus the mass of the solvent, and that fraction is times 100. So it's really the mass of the solute over the mass of the solution. Now remember, the mass of the solution is the sum of the solute and the solvent. Mass percent is used commercially, it's used industrially, and it doesn't depend at all on what the solute is. Then we're going to take a look at molarity, which is moles of solute per liter of solution. We need molarity for one of our colligative properties we're going to see later on. Now you should have already studied molarity earlier in the course. So you notice that's moles of solute per liter of solution. And then we have molality, which you probably didn't have before. Molality is moles of solute per kilogram of solvent. And molality is used for our freezing point and boiling point changes. Let's take a look at an example question. Solutions used in hospitals usually contain 500 mL of saline solution made by dissolving 4.5 grams of sodium chloride in 490 grams of water. Now we're asked to find the mass percent, the molarity, and the molality of this solution. So let's copy out the data and take a look at it. So we have 500 mL, that's the volume of the solution. We're definitely going to need that for molarity. 4.5 grams, that's the solute's mass. And 490 grams is the mass of the solvent. All right, so we'll first find the mass percent. So here's our formula. We just have to plug in our values. So we're going to have 4.5 grams, that's the sodium chloride. And now remember, the solution is the sum of the sodium chloride and the water. Oops, let me go back that, and we get 0.91%. Pretty straightforward. So make sure that you have enclosed the masses in the denominator in parentheses. Otherwise, you're going to get a wrong answer. Okay, and now the next we have is for molarity. Moles of solute per liter of solution is the definition for it. And then to find moles of solute, we have to take the mass in grams and divide it by the molar mass. Now it's sodium chloride, NaCl, and the molar mass would be 58.5 grams per mole. So what I'm going to do is make a substitution. I'm going to take my, I'm going to take my fraction here, which is grams divided by the molar mass, and I'm going to have it replace moles. So if I take this and put it in place of moles like that, I wind up getting this for a value. That's just a little bit of algebra. And this way I can put all the values in at once and don't have to worry about any rounding errors. So here I have my 4.5 grams. This is the molar mass of the sodium chloride. Notice I changed my milliliters to liters. I had to do that. And now my grams will cancel out. That'll be gone. And then moles winds up on top because I'm dividing by a fraction. So I'm going to get my moles per liter, and I get 0.15 moles per liter, which is 0.15 molar. Now we can replace the moles per liter with capital M. All right, so that's molarity. Now we have molality. You notice molality, very, very similar. So I can make that same substitution. So I substituted again, I put in my fraction grams over molar mass in place of where I had moles. So now we have grams over molar mass here, and it's kilograms of solvent. I just have to make my substitutions. And this time again, grams will cancel. Get that right out of there. And wind up with moles per kilogram. And I get an answer that's very close to molality and molarity. 0.16 for molality, 0.15 for molarity. You find that the more dilute the solutions are, the closer those two values will be. Right. Now why don't you try these three problems. Let's see if you can figure them out on your own. They're a little bit different, but it'll give you a little challenge. So pause the video at this point in time. Copy out the data from the problems. Remember, you don't need to copy out the whole problem, just the data and what you're looking for. You can see how well you can do with them. And once you've done or given up, then you can come back to the video and see the solutions. Okay, so here are the solutions. So here's the first problem. How many grams of sodium hydroxide are needed to make 150 grams of a 6% sodium hydroxide solution? So I copy out the data. 150 grams is the mass of the solution, 6% is the concentration, and I'm looking for grams of sodium hydroxide. So that's going to be the solute. Now the important thing is to write the 6% as the fraction 6 over 100, 6 grams of NaOH per 100 grams of solution. And then this becomes a conversion factor. I can write it this way, or I can invert it if I need to. Now if I just take my 150 grams, which is the mass of the solution, you can see how I can just multiply it by this and get my answer. And you notice that my grams of solution will just cancel right out. So it's very easy, but this is the key step right here, writing this thing as a fraction. So we're going to be doing that with all of these different problems that involve either percent, molarity, or molality. All right, let's take a look at the next question. A student evaporates 55 mLs of 1.6 mole of potassium chloride solution. How many grams of potassium chloride remain after evaporation is complete? So I copy out the data. 55 mLs is the volume. X grams KCl is the unknown. 1.6 molar is my concentration. So again, I'm going to write 1.6 molar as a fraction. Oops, so I did too fast. So it's 1.6 moles of KCl per liter. So I can take my volume then, and I'm going to write my 1.6 moles per liter like this. Here's my fraction. And when I multiply it by my volume, convert it to liters, you notice that I get moles of KCl for an answer. There go my liters. So I had to know to move the decimal point 3 places to the left. That's why we get that 0 in front. 3 places to the left to get in liters. Then they'll just cancel out. Now once I have moles of KCl and I want grams, I can just find the molar mass of KCl and then multiply it by the number of moles. And the molar mass is 74.6 grams. And then again, we can cancel out moles. And I get grams for an answer. Again, the key step, we're writing this as a fraction. A lot of people don't do that, and then they just don't see capital M as being anything. So you really have to write that as a fraction. All right, now for the last problem. What's the molality of a 12% glucose aqueous solution? All right, so again, we want to write the percent as a fraction. So 12% is 12 grams of glucose per 100 grams of solution. Now notice in the problem they didn't give us any amount of the solution, and that's because it doesn't really matter. So we're going to make some assumptions. I'm going to say, well, if I had 100 grams of the solution, that would be 12 grams of glucose. So remember, the concentration does not depend on the amount of the solution. So molality means moles of glucose per kilogram of solvent. That's what I'm trying to find. So I have to be able to take my grams of glucose, that would be 12 grams of glucose, and I'm going to convert that to moles. It won't be too hard, just get the molar mass of glucose. I have the formula up here, so that'll be easy. And but I have 100 grams of solution, and this isn't solution, it's solvent. So I'm going to have to find my grams of solvent and then convert it to kilograms. So to find the moles of glucose, I take my 12 grams and divide it by 180, which is the molar mass, and I get that many moles. So I'm all set there. Now to get my kilograms of solvent, I'm first going to have to get grams of solvent. So I take my grams of solution, I subtract my solute from it, and I get my water, which is the solvent. And then by dividing this by 1,000, when I divide this by 1,000, I wind up getting my kilograms. And then I just have to take my fraction. I want moles of solute per kilogram of solvent. Plug it in, I get my answer. So I get 0.76 moles per kilogram. We can write that as 0.76 small m, which means molality, and we read it as molal. Right. Now here's a problem that you find a little challenging. One more to go, and if you want to try this on your own, then pause the video at this point in time, take out a sheet of paper, and give it a go. Otherwise, I'm going to go through the solution with you. So a lead storage battery is 3.75 molar sulfuric acid solution. That's a density of 1.230 grams per milliliter. Find the molality of the acid solution. And this is pretty much a fully charged battery. Okay, so find the molality. So we need moles of solute per kilogram of solvent. And you notice what they give us. They give us molarity, which is moles per liter, and this is grams per milliliter. So we need the density because this is going to give us a volume, and we have to go from a volume to a mass of solution so we can wind up with the mass of the solvent. Let's see how we do that then. So we write the molarity, 3.75 molar is 3.75 moles per liter. So I'm going to find the mass of the solution, mass of solute, and then mass of the solvent. So the first thing I do is I'm going to take my density, 1.230 grams per milliliter. Now multiplying it by 1,000 milliliters. Now you might wonder, why did I get 1,000 milliliters? Because that's the definition of molarity. So I have to make assumptions all the time here. I'm assuming then that I have a liter of this battery acid. So a liter of it would be 1,000 milliliters. And then 1,000 milliliters of this acid would weigh 1,230 grams. So that's my assumption that I have a liter of it. Now, if I want to get, I have to get the number of grams of solute so that I can subtract it from the grams of the solution. So to get the grams of solute, I take my number of moles, which is from the molarity, and I multiply by the molar mass of the sulfuric acid. Now you might say, well, I didn't know that. Well, usually you'd be given a formula. So this is the formula for sulfuric acid. It's H2SO4. You could have always looked that up, but you have to get the molar mass anyway. Now, once I have my grams of solution and my grams of solute, I can subtract these to get the mass of the solute. And you notice that I get 862 grams of solvent, which becomes 0.862 kilograms of solvent. So now I have my kilograms. That's what I need. It tells me up here. I need my moles of solute, which I started off with. So straightforward then. And I get 4.35 moles per kilogram of 4.35 molal. So here's how you can go from, molarity to molality. Now the last problem went from percent to molality. Okay, and that's going to be the end of the show.